The air conditioning didn't work when it got warm. So they built up this platform up in the front, and so we could walk back and forth over with them. And the difference between then and now is that the microphone we had then was wireless. Okay, so you see, after 30 years, the advances we're back to that. Well. We had a lot of fun teaching back then. Teaching at a state university is a little bit different than teaching here at OIT. Teaching at a state university is all formality, and I guess if I'm among friends, I can say this. But most universities, what you've got is a faculty that desperately needs experience. They have never been forced to earn their bread and butter by practicing the profession that they're teaching. They learned it out of a book from their professors, and now they're turning around, they're teaching it to you out of a book. But nobody's ever done this stuff before. They have no experience and no feeling for what they're doing. In teaching here at OIT, it was the other way around. The faculty, my colleagues, almost everybody came from industry or had industrial experience somewhere, And so it was a lot of fun teaching here at OIT. And I remember a lot of the students were people that were just coming back from, they got to realize this is the early 70s. They were coming back from Vietnam and trying to put their lives back together and, gain an education and something practical that they could do. But I'll never forget one day teaching at, over on Main Street there. I was teaching, it was on a Friday afternoon, I was teaching a class transform. Systems theory, voting watts and all that. And, working away at just like this, working away at the blackboard, there was a pencil sharpener here. And the big guy came in, right while I'm working his lecture, Friday afternoon, you got to realize 100 degrees in that room. Poor students are all laying there, half asleep, laying there with one eye pointing one way, the other eye pointing the other way, trying to take notes. And this guy walks in, whoop, that's all right, don't worry about it. He walks in and sharpens his pencil in the middle of my lecture. And then I stood there looking like, what do you think you're doing? I'm not going to let him get away with this. So I went running out in the hall after the guy. And I, big guy, what do you think you're doing? He was looking me down at me, And you could tell something was wrong. He spaced out. And he walked to the next room in the back of the next, and Alex Misha was in there. You're teaching a class. And the next room went a long ways, parallel to the hall. We were up on the platform in that room. And the guy comes to the back of the back room, and he flashes the P symbol and stuff like that. And he turns around and he walks out. I thought, I gotta go for help. So I left my class behind. I ran down the hall, and this was at Main Street there. We went in the back door, went through where the faculty space was, and I thought, who do I tell? How do I get help? And the dean of it was the guy from Chicago that, I can't think of his name, he's the one that changed his name. What's it? What? Yeah, something like that. He's sitting at his desk, and I go running into his office. He was the dean of something at the time. And I said, there's this guy out there who's running around doing this or whatever, And of course, he was busy, and he's working away. He looks up at me like, Corum, don't worry about it, everything's going to be all right. What are you talking about? I said, there's this guy out there, he's running around going like this. And the guy walks right into the dean's office and moved right down, and turned around and walked out. And walked out right onto Main Street, he was gone. We never saw him again. And just somebody walked right in off the street. And so I went back to my classroom, and there are those guys, and they're all sitting there all still asleep. They didn't know anything happened.
That was the baby hippie.
Say things haven't changed here. All right, look, let's talk about Tesla coils for a little bit. If you've been over to Ohio State, you've seen this machine. We had it at Battelle for a number of years and got some wonderful results with the thing. And when I left, Battelle was going to junk the machine. I said, oh, don't do that. So I ran over to see Stephen Sebo, Professor Sebo over in the power engineering department over there at Ohio State, a wonderful man. And I remember when Professor Sebo came to OSU back in the late 60s, he came, I think, from Columbia. His power engineering was his specialty. And anyway, this machine's now over there. You may have seen it, but this is an equivalent circuit board. The circuit doesn't look like this. Of course, it's got a nice power control system. But this is essentially what's going on. It's about a 35 kVA machine, nice big power transformer. I think we actually have 2 0.12s here, so it's actually about 0.24 microfarads. So we charge 50 kV with this rotary spark gap. It actually has 2 tungsten spark gaps. Unfortunately, the spark gap duration, we never got that down below about 100 microseconds, which is bad. Test out of Colorado Springs is working spark durations around 20 microseconds. I hope we have time to talk about that tonight. Let's see. Let's make a ground rule here. I don't want to wear you out and wind the professor up and he runs for an hour and then rewind and then run for another hour. Why don't I stop at, say, 8:30? Is that all right? You guys last that long? You can do it, Bill. Well, I know I could, but
Want to come back next week?
Right. But this resonator is a critical piece, and this ground is important. Realize that what we've got is a primary. That's this guy right here. That's tuned, and this resonator was, I believe this is 8 feet high, sitting on a 4-foot platform. The rotary breaks and the capacitor and all that junk is down here. This toroid is 4 feet in diameter, and I think it's flipped this way. I forget how many picofarads, sitting up there on top. So the whole structure is about 13 feet high. When we had it in the lab in Battelle, was it building A, I think? No, I'm sorry, building 1. Yeah, it's kind of funny at Battelle. They numbered the buildings in the sequence in which they built them, see? Well, they start with building A, and then they built building 1. When they opened up. And this was in building 1. What?
It's like car talk.
Yeah.
Part 1 and part 2.
Right.
And Roman numerals 3.
The click and clack. Yeah. I understand they did part of the Manhattan Project in this very place where this experiment was, set of experiments was going on. Realize I've got it down for you can see we've got a 5-ton overhead lift here. That was really nice. The building's about 300 feet long this way. I think it was 50 feet this way, 25 feet high. This is at 13-foot level. These dischargers are about 10 feet up to the girder up above there. And we took these from a step ladder. I think it was a 16-foot fiberglass step ladder, so it was insulated. And this was the very first time we operated the thing. So at this point, it wasn't tuned up. We weren't really getting nice big sparks, and we weren't getting it to do what we wanted it to do. But this is the first picture we had of the thing.
Tell them about who was trying to be sensitive magnetic measurement on the floor above.
Oh, yeah. I'd forgotten about that. Just above us was a sensitive magnetics metrology lab. And, we're talking about maybe a foot of concrete between us and them. And, of course, whenever we fired off, strange things would happen. They didn't know what was going on at first. I forgot about that one. This is I get it oriented right here. We had some really nice guys that were in that lab. It was a metals processing lab, and Battelle was going out of that business. So we were able to use the space that they had. Some really nice people there that assisted us in every way possible. This again is this was taken just for your entertainment. This is the kind of discharges we had back then. Down below this thing is, again, it's a 13 feet high, and this is 8 feet on top of a 4-foot platform. This is an oscilloscope. We just used the oscilloscope as a field detector. Wasn't connected to anything, it's just a tube. You just set the tube there to light up, all right? Like a fluorescent bulb or something, but it was kind of nice because we could tell when we had high fields before we had the discharge. This is wasted energy. You'd like to be able to direct the discharge. So you'd like to have a directed energy weapon. You know, Department of Defense calls them DEWs. A few years prior to this, we had in a lab up near Cleveland, in Windsor, Ohio, we had, actually I guess it was in Newbury, Ohio, we had been doing the work that, we've been reading through the end of Tesla's diary. And it's in the back. Let's see, when is it? The dates are, I'm thinking along about December of 1899, where Tesla's describing the production of fireballs. And he's saying, you do this, and you do this, and you do this. And then he goes to the next period. And then we could see the fireballs and stuff run on. Okay, so we built the apparatus. This is the electrode, this on top of a apparatus. See, we found that we could make these fireballs with very low power. You don't need, people try to crank up their machines to make, the trick to making fireballs is to use relatively low power, only a couple of kilowatts. So we did what he said in the paragraph, and we weren't seeing the results. I mean, we did A and B and C and D, just like he says, and where he says, and then you see the fireball, and we saw nothing. And we kept playing with it, tuning with the thing, and then paying attention, careful attention to what he said. And as you do what he said to do, all of a sudden they begin to appear. And again, what happens is they actually spit out, just like somebody took a handful of lighted ping pong, blew them out, and the discharge would follow them. What's happening is we're actually having a spray of them. These are about ping pong ball size. It's about 20 feet from here to here, and we're back about 16 feet in this direction, taking a picture of this. We wrote this up, I think it was in 1990, and that's when I couldn't get anybody here in the U.S. interested in this stuff. We talked to experts on lightning and so forth down in Florida. I can't see the guy's name right now. I wrote the book on lightning, Mark Newman. And he said, well, it looks more like low lightning than anything I've ever seen, but I'm not ready to bless it yet. Well, good for you. I wrote an article on this and sent it to Nature. And got an incredible review back to Nature. Some guy in England reviewed it. He said, "Oh, these photographs are obvious frauds. This is not, can't be done." And well, all right. The heck with these guys then. I've written an article, told them how to do it. All they have to do is go in the lab, do it themselves. And if they're not willing to do that, then I've got other things to do. We sent a copy of the paper off to a symposium at Novosibirsk, a ball lightning, European ball lightning community. And those guys got really excited. That's when we got invited to go over to Moscow, because there was a lot of work going on in ball lightning over there, pulse power RF systems. The photographs and the articles have been picked up by Stanley Singer. And Singer's the guy that wrote the book on ball lightning back in the early 80s. He has another book that will be published by Springer Verlag, and our material finally will appear as a chapter in his book on ball lightning. When will the book be out? Every time that we talk to him, he says, "Oh, I'll have it ready in another 6 months."
So, do you have a theory to explain how ball lightning, what's the structure of?
Yeah, there's several different theories as to how this thing could happen. We call them electrochemical fractal structures. The trick to ball lightning, to explaining ball lightning, not to making it, there's no trick to making it. Well, you do what Tesla said, but any theory that you have, it's got to do two things. Ball lightning emits energy very rapidly, right? But it also has a long lifetime. So it's got to be able to emit that energy hold it back, and it's got to be able to throttle it so that it only lets out so much at a time, so that it has a lifetime that's a certain length. Now, over the years, people have chronicled typical lifetimes. And lifetimes run the order of about 1 second out to 10 minutes. Now, when you plot the curve, and Finkelstein does this in one of his papers in Journal of Applied Physics, I think back in the late 60s or so. What you actually get is a distribution that looks something like this. In the meantime, it's about 2 seconds. 10 minutes out here and a tenth of a second or so in here. What we did is we took videos of this. And then you can count the frames to see how long the thing actually lasts. And typical lifetimes on ours were right around 2 seconds. Matches right in real well. Now, the next question is, all right, if that's the criteria, that you've got to be able to, whatever the reaction is, whether it's chemical or mechanical or what, acoustical or what is it, you wouldn't believe how many papers, theoretical papers, have been published on all that. Let's see. I recall a physics professor at Clifford here at WVU making the comment about general relativity. No, it wasn't Clifford here. It was the guy who did the gravitational waves from University of Maryland.
Weber?
What?
Weber,
yeah. Joe Weber. We had him come, by the way. He was an IEEE member. He was an electrical engineer turned physicist. What got him into general relativity was the instrumentation for gravitational wave detectors. He picked up the general relativity on the way. But Weber made the comment that he said, general relativity, the ratio of experimental papers to theoretical papers is an incredibly tiny number. Now, back then, I think when he said this was in the early 70s, the total number of papers on general relativity, I think, came to about 10,000. I think it's quadrupled since then. Everybody writes papers on general relativity today. Whole journals associated with it. Well, the same thing with ball lightning. There's just an incredible number of papers on theories of ball lightning. And then you get a lot of these ones that describe observations. And inevitably, the ones that are describing observations and personal experiences with it are, I saw this big flash, and I heard a bang, and something bounced around and flashed of light, and was nothing less but a greasy spot and a bad smell. And that's virtually every experience with ball lightning that's it. They just say the same thing in 1,000 different ways. What we found is this. Tesla was using copper electrodes, and he describes the surrounding of the copper electrode as he describes it as heavy, heavy rubber dielectric. Okay. Now, you've got to realize rubber back then was mostly soot. So carbon was involved with this thing. And right in the late 80s or so was when people began to look at these carbon puffballs. And there was a wonderful theory that some guy in Russia had come up with if you had carbon in the presence of rich ozone, ozone got absorbed into these puffballs and gave you, the release of the energy was very slow from this thing. So you could have intense energy and yet have it released at a controlled rate. So, it didn't all pop off at one reaction. So that was kind of the explanation that we used back at that point in time. However, somebody said, well, is it possible that it was some kind of charge distribution, like a donut or something like that? And one of the things that we did, and you can't see it in any of these pictures, but that's not with me tonight, but when you take these things and blow them up, it's really kind of interesting. They do indeed look like fat toroids. With, you can see where the discharges come and dimple them on one side. And so maybe there is indeed all of this hypothetical stuff, but maybe there is something to that. All I know is this, that if you want to make ball lightning, you can do it a number of different ways at home. The easiest way to do it, I should tell you this. Michael Faraday in 1863, I think, wrote a book called The Chemical History of the Candle. And Faraday was very interested in, how does a candle work? All the colors you get and all that stuff. And, he goes through it. He presented this lecture, the Christmas lecture there at the Royal Institution, I think that was it. And it was later then transcribed and prepared for children. But it's a marvel. You can buy it in bookstores. I'd be surprised if they don't have it in orders bookstores. The Chemical History of a Candle. And if you take a regular candle, bring, say, a fork or a screen down over it, what'll happen is you'll have the flame of the candle underneath the screen, and above the screen, you'll just get all this carbon coming off. That carbon, of course, is what's important for it. You take that carbon, and you put it near a discharge here, we begin to get all these fireballs. It isn't enough that you just put the carbon there. You've got to have ozone present. Okay? So get your machine up, get it going, get lots of ozone around. I should tell you this little story on the side. While we were doing this up in Newbury, the lab we were in was a large lab. It was one of these buildings with the steel girders and stuff. Probably about 5 or 6 times the size of this room with a higher ceiling. And so we had the thing fired up and lots of ozone present, but it was in a contained area. And we found out, and it's one of the things that chemists know, but us poor dumb PEs didn't know it. Ozone is a very powerful laxative. And all of a sudden, you can realize it took about 15 minutes, but all of a sudden, 10 electrical engineers, all they did use the restrooms all at once. So you want to get a lot of ozone present. Okay? And you can use a pencil or charred piece of wood as an electrode or copper. And the thing is, there are 2 types of fireballs. They're the ones that occur in submarines. And those are high current discharges where you get the fireballs to occur. They also occur in diesel locomotives, where you've got very high current. And then there are these high voltage ones, where again, you're getting high current, but it's when you take your high voltage and you discharge it, bring it down to 0 real quick and get a lot of current. And that's what you want. And you get a whole of these things, and out will spurt off of these fireballs. And the fireballs will spurt out, and then the discharges will follow them. Now, that following of the discharge was of significance to us, because how do you make lightning go in how do you point lightning and go bing and things go there? Lightning wants to go all over the place. Say, well, maybe I could just put a wire up there. And here's a photograph we have of a wire connected to the top of a Tesla coil. And let me pull this out, because we may be losing a little bit. You can see that the thing about, if you raise the voltage on a wire, of course, you have a very sharp curvature on the wire. Again, this is in building 100, late at night. We've got this wire. I think I have this in backwards. Yeah, that is the way it looks. Okay, so the Tesla coil was up here, and here's the wire going, this is about 4 or 5 feet over the top of the fence going over to the other side of the thing. And the wire is about 30 feet long or so. And of course, what happens is because you have very intense E fields near the curvature of the wire, air is breaking down, and you're getting an electron collision back, and so you're getting all this electric blue discharge. You get all corona. So you can't direct your discharge with the wire. So shooting a wire out, then firing a hard, large voltage down the wire doesn't do it, because the E field is perpendicular to the wire. But if you could spray some macroscopic particles, this is the top of the discharge of the electrode here. And suppose we could throw out a bunch of macroscopic particles. By macroscopic, we mean in the range of 1 to 100 microns. Right? So it's dust. Then maybe the fields would follow that as opposed to being perpendicular to it, see? So the idea came, well, all right, we could spray our fireballs. Maybe we could direct the discharge, and we'd have a directed energy weapon. So you could point it over there and pow. Tesla had this is about 27 feet here. But we've got the same thing. We've got a distribution of insulated conducting particles sprayed along a trail, and the electrical discharge follows them. So now you've got a way to keep your energy from going all over the place, like it was in one of those earlier pictures that I had. You know, so you can go from that to that, right? If you had a gun that would shoot the particles. Now Tesla describes such a gun.
Doctor, could you give some duration of that charge?
How long? Oh, let's see. Those are probably on the order of half a second blast. One of the last things that Tesla works on professionally in the 30s is this. He comes up with a gun to spray these kinds of particles. And there's a paper, you can get it probably on the internet, a paper of a memo that he gave, where he describes this gun that he's using, where he's squirting out these little particles from inside the electrode and so forth. These are hypervelocity charged Macrons that he's using, so he's sending out them very fast. Hypervelocity means they're much, much faster than the speed of sound in the medium that you're in, 10 to 15 kilometers per second. So these are meteors. Now the problem with meteors is that they burn up in the air. So he sends along a whole stream of these things, one after another in the channel. And I'm going to skip this part because it takes us in another direction that we want to go tonight. No. I want to get you the good stuff. Yeah. How much? I haven't given you any arithmetic yet. Right, you got to have some analysis. I mean, it isn't science to tell you to write some equations and perform an experiment and check the equations. Seems to understand what's going on. Yeah. So let's go in that direction for a little bit. Okay. If we look at the circuit that we previously had, you know, I wonder if I've got. Sure I do. I don't want to just throw equations at you and not show you the circuit diagrams so you see why we're doing what we're doing. And I know I've got it right here. Yeah, it's this one here. All right. Look, here's what we're trying to analyze, this circuit. Okay. By the way, there are a whole bunch of different ways you can analyze this. And depending upon who you are, you will approach this circuit a different way. For example, if you were just an ordinary dumb sophomore and you don't know any better, you would sit down and you'd write the Kirchhoff voltage laws on this side and this side. And you get a sort of answer when you do that. Not being, the problem is a lot of us are kind of tainted by our graduate study, and we want to be a little more elegant. Right? So instead of just writing Kirchhoff voltage laws, what we might do is use Lagrange's equations. All right. In fact, I got a phone call one day while I was at Battelle from a professor at the University in Holland. And he says, "Oh yes. He says, I'm going to do it by the principle of least action." And I said, "Go ahead and see what you get." And I got a phone call back again from Holland about 2 weeks later. It took him that long to work this thing out. He says, he says, even the dumbest sophomore would have known better. He says, of course, you get the same result as if you use Kirchhoff's voltage laws. Where do you think Kirchhoff's voltage laws come from? You apply the principle of least action to Maxwell's equations for a circuit, and out comes Kirchhoff's voltage laws. Of course. Feynman has a nice discussion of this in the Feynman lectures on physics. Okay. So you can use Lagrange's equations, the principle of least action, and Kirchhoff's voltage, whatever you want. You can do it. But we're going to put it as a lump circuit first, and then we'll see that it doesn't quite work that way equal through. But you'll get the same result. I mean, Kirchhoff's responses are fine. They work great for double E's. So what do? Well, you sit down.